Dear students, I welcome you for the today's class related to boundary layer conditions and their numericals. Yesterday we have seen the hydrodynamic boundary layer and the thermal boundary layer. Today we will be solving some numericals associated with that. For low values of Reynolds number, when you consider a boundary layer, that is, if this is a plate and the fluid flow is coming from this direction with a uniform velocity of u infinity or the capital V, there exists a certain boundary layer and which is going to increase in its thickness. Now this is what delta we have defined. This is the boundary layer delta for which we are considering the hydrodynamic boundary layer, and this thickness delta is at a distance of x. What is the value of x? X is the distance of the plate in the x direction and delta is the boundary layer thickness. This understanding is needed. Now if you will calculate the thickness of boundary layer at this distance, it may vary. So depending on the distance, the thickness of the boundary layer that is going to vary. Now in case of a low Reynolds number, that is the laminar flow condition, the Reynolds number is low, the value is 10 to the power minus 5, that is below 10 to the 5 into 10 to the power minus 5. If the values of Reynolds number are below 10 to the power minus 5, this is the value of Reynolds number. Then we are using this formula delta. This is nothing but your hydrodynamic boundary layer 5 times the distance of a plate. That means we are calculating the distance from the distance. At what distance I am going to calculate? This is a plate and this is what the distance x that is there, and I am going to calculate the thickness of boundary layer at this distance. This is the x and this is the delta. So 5 times the length upon the Reynolds number at that length raised to the power 0.5. So this is what the thickness of a boundary layer, hydrodynamic boundary layer, that is calculated. Now there is a relationship between the hydrodynamic boundary layer and the thermal boundary layer, and this is depending on the Prandtl number. Prandtl number is Cp mu upon K. The thickness of a thermal boundary layer that is calculated or considered as delta Th. Delta is your hydrodynamic boundary layer, or sometimes this hydrodynamic boundary layer is also represented by delta H. H is for hydrodynamic, and this relationship between the thermodynamic boundary layer and the hydrodynamic boundary layer, that is thermodynamic boundary layer which is equal to the hydrodynamic boundary layer thickness upon the Prandtl number raised to the 1/3. Then next is the calculation of the heat transfer coefficients. For that purpose, you are having the different relations. First, we have already discussed the dimensional analysis, which is incorporating the different relationship between the Nusselt's number, Reynolds number, and the Prandtl number. This is the relationship between the Nusselt's number, Reynolds number, and Prandtl number. So this is one of the relations for specific conditions, that is the local heat transfer coefficient at laminar condition. Then if the boundary layer, hydrodynamic boundary layer, if it is the turbulent conditions, then what will be the formula? That is delta Hx or delta, which is equals to 0.381 times the distance upon the Reynolds number raised to 0.2. So this is the hydrodynamic boundary layer thickness for turbulent flow conditions, and this relation is for the laminar condition. Now there is also few things that is needed, is the equivalent diameter. Now in equivalent diameter, why you require the equivalent diameter? Because our different formulas of require the or are defined in terms of the Reynolds number. However, the flow that can flow through the pipe where the diameter is specified, but when the diameter is, say for example, outside the tube, outside the pipe, there are n number of pipes, and the fluid flow that is flowing through outside of the pipe. So what will be its effective diameter or equivalent diameter? Sometimes the fluid passes through a square section or through a rectangular section. Then what will be its equivalent diameter? For that purpose, we are having one formula to calculate the equivalent diameter, which is equal to 4 into cross-sectional area upon the weighted perimeter. 4 into cross-sectional area upon weighted perimeter. So this is what is the equivalent diameter that is defined. 4 times the cross-sectional area upon the weighted perimeter. So equivalent diameter for the annulus section. Annulus section is what? There are two pipes. One pipe is inside and above that there is another pipe. So what will be the diameter for this section? Equivalent diameter for this section. You are knowing this diameter. You are also knowing the outer circle diameter, but we are not knowing the diameter which is the inside in between these two pipes. So that is calculated in terms of a equivalent diameter. So that is called a annulus section. So this is the equivalent diameter of an annulus, that is calculated as 4 into cross-sectional area upon weighted perimeter. So cross-sectional area in this case pi by 4 d square, capital D square is the outer diameter and small d is the inside diameter. So this is capital D square minus small d square upon perimeter is pi d plus pi d. This is what? The perimeter is nothing but your circumference. Inside circumference and outside circumference. That is what is the weighted perimeter. Then equivalent diameter of a rectangular duct, that is 4 into cross-sectional area upon the weighted perimeter. 4 into cross-sectional area is length into breadth upon the 2 times the perimeter, 2 times the length plus breadth. So this will be its equivalent diameter. Similarly, you can also calculate for the square also. So equivalent diameter for a rectangular annulus. So inside there is a pipe and outside there is a rectangle. For that also you can calculate the equivalent diameter for the annulus in a rectangular cross section. Now to calculate the different heat transfer coefficients for the fluid flowing inside the coil. So now we will consider the different numericals associated with this, the boundary layer examples that we are going to consider now. A smooth flat plate is heated A smooth flat plate is heated to a uniform temperature of 110 degrees Celsius at 23 degrees Celsius with a uniform free stream velocity of 19.5 meters per second. That means the temperature of the heated plate that is mentioned, which is 110 degrees Celsius. Then the air at 23 degrees Celsius, this air at 23 degrees Celsius, which is having the uniform velocity of 19.5 meters per second that is mentioned. Then calculate the length of a laminar boundary layer over the plate, one thing. Then the thickness of the hydrodynamic and the thermal boundary layers at the critical length. Third, the local heat transfer coefficient at a critical length, the average heat transfer coefficient over the portion of the plate covered by the laminar boundary layer, and the total heat flow per unit area in the watts. So this is what our figure mentioned. 110 degrees Celsius is this plate temperature. Air that is flowing at a 23 degrees Celsius, which is having the velocity of 19.5 meters per second. These are the properties of the air, that is density of air 1.029 kgs per meter cube. Specific heat is the 1009 joules per kg Kelvin. Thermal conductivity of the air is 0.0296 watt per meter Kelvin. Viscosity of the air is 2.04 into 10 to the power minus 5 Newton second per meter square. So these are the physical properties of the air. Now, at a critical Reynolds number, what critical Reynolds number? That is the transition from laminar to the turbulent conditions. So this is what the critical Reynolds number, which is equal to the 5 into 10 to the power 5, that is considered as the critical Reynolds number, and it is represented by REC. So length of this boundary layer at this critical Reynolds number, that is to be calculated. Reynolds number is having the formula of x u rho upon mu, which is equal to 5 into 10 to the power 5. So we are going to calculate this x, the length. At what length this Reynolds number exists. We are knowing the velocity of the fluid, that is 10 to the power 19 into 5, 19.5 meters per second. We are knowing the other physical properties, that is density and viscosity. So at what length I will get this Reynolds number of 5 into 10 to the power 5. So with this exceed critical Reynolds number by simply substituting the value of Reynolds number, the viscosity and velocity and your density. So I have calculated this as the 0.508 meters. So this is the 0.508 meters is a critical distance, critical length where I will get the Reynolds number as 5 into 10 to the power 5. That is the length of laminar boundary layer. Length is different and thickness is different. Now from this length we are going to calculate the thickness. So considering this as your laminar condition, that is the formula delta, which is equal to the 5 times the thickness, 5 times the distance upon the Reynolds number raised to 0.5. So you will get the hydrodynamic boundary layer thickness as 3.593 into 10 to the power minus 3 meters. So that means it is in the millimeters, 3.5 millimeters. A small thickness you can imagine here, a small thickness of 3.5 millimeter. Now, from this thickness of a hydrodynamic boundary layer, you are going to calculate the thickness of a thermal boundary layer. And our formula for thickness of thermal boundary layer, that is calculated as delta TH, which is equal to delta upon Prandtl number raised to 1/3. So this is what the hydrodynamic boundary layer thickness upon the Prandtl number Cp mu upon K. So its value is 4.05 into 10 to the power minus 3 meters. Now you are knowing the thickness of a thermal boundary layer and the thickness of a hydrodynamic boundary layer and the distance x, that is the critical length. This is all our calculations related to the critical Reynolds number of 5 into 10 to the power minus 5, where the transition from laminar to the turbulent flow conditions that is taken. So then next is calculation of the heat transfer coefficient, Hx, which is the Nusselt's number is equal to 0.332 into Reynolds number raised to 0.5 into Prandtl number raised to the 1/3. So substituting the value of Reynolds number, substituting the value of Prandtl number, you get, and substituting the value of thermal conductivity and the distance x, the heat transfer coefficient that comes as the 12.12 watt per meter square Kelvin. Then next that is asked the average heat transfer coefficient. So 2 times this local heat transfer coefficient, this is what the local heat transfer coefficient that is calculated. So the average heat transfer coefficient, that becomes the H average, which is equal to 2 times the Hx. Or you can also calculate the Q, which is equal to HA delta T. So H, that is this value, area for the plane, that is your cross sectional area, that can be taken as, and the temperature difference. From there you can calculate the total heat transfer in the watts. Then coming to the next example. For the turbulent flow, a tube with no change in temperature of the liquid and the tube wall, how will the heat transfer coefficient change? This is for the turbulent flow in a tube with no change in temperature, that means your delta T is constant, and the tube, how will the heat transfer coefficient will change if the diameter of the tube is tripled, keeping the velocity constant, And second, if the 3 times increase in the fluid velocity, what will be the change in the heat transfer coefficient that one can calculate. So our formula, that is Hd, which is equal to 0. Nusselt's number, which is equal to 0.023 into Reynolds number raised to 0.8 into Prandtl number raised to 0.33. So this is our formula for to calculate the heat transfer coefficient in turbulent flow condition. In turbulent flow condition, this is equation is called the Dieters-Boelter equation. Dieters-Boelter equation, and this is used for turbulent flow conditions. So I can write this Reynolds number and diameter and the thermal conductivity. Reynolds number, that is du rho by mu raised to the 0.8, and this d is there. This d will go in this direction, so value of d will be raised to the 0.2. This is also the capital D raised to the 0.2, and mu will have the value of 0.8. Rho upon mu will have the value of raised to the power 0.8, and Prandtl number, that will remain the constant because this is depending on your physical properties. Cp, mu upon K, all these are your physical properties of the material. So Prandtl number is not going to vary. So varying parameters are the velocity and the diameter. That is why we have correlated this velocity and diameter. This viscosity and the density, they are also the physical constant. They are not going to vary because the same fluid that is going to pass. Now the first condition is that the diameter of the tube, that is tripled. So we are changing the diameter of the tube. So H1 and the diameter, they are inversely proportional. So H1 and the diameter, they are inversely proportional to H2 and D2. So your equation, that H2 will be 0.8 times the H1. That is, even though the diameter of the tube, that is tripled, we are increasing the diameter, keeping the velocity constant, the heat transfer coefficient, that decreases. Keeping the velocity constant, increasing the diameter of the tube reduces the heat transfer coefficient. This is the conclusion that we can draw from this. So it is better to use the smaller diameter tubes to get a higher heat transfer coefficients. For smaller tubes, for smaller diameter tubes, you will get the higher heat transfer coefficient, but at the cost of higher pressure drop. Higher pressure drop, that means your operating cost, that is also high. The next is again the heat transfer coefficient. The second condition is that 3 times increase in the fluid velocity. Now I am increasing the fluid velocity. So fluid velocity raised to the 0.8, they are directly proportional. So H2 heat transfer coefficient, that is increased 2.4 times the H1. However, the velocity, that is increased as the 3 times. That means even though I am increasing the velocity with the 3 times, my heat transfer coefficient doesn't increases 3 times. It increases only 2.4 times, keeping rest of the things as the constant. So selecting the suitable velocity is also important in case of the heat transfer coefficient calculations. The next example, that is related to the boundary layer. An oil at 110 degrees Celsius flows over a plate. This is what the plate that is available. The oil that is flowing at 110 degrees Celsius The plate that is maintained at 50 degrees Celsius, the velocity of the oil is 1.5 meters per second. The velocity of the oil, that is 1.5 meters per second. Calculate the hydrodynamic and the thermal boundary layer thickness at a distance of 0.6 meter. Now in this example, the distance that is mentioned, the Reynolds number that is not mentioned in this case. The distance that is mentioned in this case. The previous example, the Reynolds number, critical Reynolds number, we have assumed. For that, we have calculated the thickness and then the hydrodynamic and thermal boundary layers. Now, we are going to calculate the Reynolds number, whether it is laminar or whether it is the turbulent flow condition. So the Reynolds number for the oil flow over the plate at a distance of 0.6 meters, 0.6 meter, that is what it is mentioned here, 0.6 meters. So Reynolds number, velocity into density into the distance x upon the mu. Velocity is 1.5 meters per second. The density for the oil is 853 kgs per meter cube and the velocity is 0.6 meters per second. The viscosity is 0.0356 Newton second per meter square. So Reynolds number coming as the 21,500. Now calculation of the hydrodynamic boundary layer. So it is below 5 into 10 to the power minus 5. The hydrodynamic boundary layer thickness, that is delta Hx, which is equal to 5 times the distance upon the Reynolds number raised to 0.5. So this thickness of the hydrodynamic boundary layer, that comes as the 0.02 meters. Then calculation of the thermal boundary layer thickness, that is delta Thx, which is equal to delta Hx upon Prandtl number raised to the 1/3. So that comes as the 2.45 into 10 to the power minus 3 meters. Next is the local heat transfer coefficient calculations. That is the Nusselt's number, that is nothing but H x upon k, which is equal to 0.332 into Reynolds number raised to 0.5 into Prandtl number raised to 1/3. That comes as the 91.7 watt per meter square Kelvin. So this is what the local heat transfer coefficient. The average heat transfer coefficient is 2 times the local heat transfer coefficient. Now this is one of the relations that is used to calculate the heat transfer coefficient. Then there are the other relations also. However, this relation corresponds to the value of Prandtl number between 0.6 to 50. This relation corresponds to the value of Prandtl number between 0.6 to 50. However, in this numerical, the Prandtl number is 546. So we are using a different relation, that is Nusselt's number, which is equal to 0.339 Reynolds number raised to 0.5 into Prandtl number raised to 1/3 upon 1 plus 0.047 upon Prandtl number raised to 0.67 raised to 0.25. By using this relationship, the Hx, that is calculated as 93.59 watt per meter square Kelvin. Now comparing these two values, 97, 91.7 and 93.59. So they are nearly more or less same, only difference of 2% that is there. So heat transfer coefficient values, they are not fixed, by which relation you are going to calculate, that may vary. That may vary depending on the flow conditions. That may vary depending on the surface conditions. So if I am purchasing a pipe, new one, it may have the higher heat transfer coefficient values initially. But with the progress of time, that pipe may corrode and form the additional resistances. Some deposits may be there on the pipe. So again, that is your fouling resistance that will be there. So both the things are going to affect your heat transfer coefficient. So with the progress of time, my heat transfer coefficient that may decrease. So it is a function of a time as well as depending on the different variables. Now the next example, a duct we are considering. A duct of an air conditioning system has a rectangular cross section of 30 centimeter by 45 centimeter. The air at 18 degrees Celsius is flowing through the duct at 8 meters per second. Estimate the heat leakage from the duct per unit length per unit temperature difference. So first I am going to draw a rectangular duct having the distance of 30 centimeter on this side, 45 centimeter on this side, and if 18 degrees Celsius is the temperature, and the velocity is the 8 meters per second. Velocity is 8 meters per second. So this is a rectangular. What will be its equivalent diameter now? So for that purpose, we are going to calculate the equivalent diameter of a rectangular duct. So this is 4 times the cross-sectional area upon the wetted perimeter. Cross-sectional area is length into breadth. Upon the perimeter is the length plus breadth. 2 times the length plus breadth. So the equivalent diameter, that is 0.36 meters. So this is what? The 30 centimeter. This is what? The 45 centimeter. So my equivalent diameter, that comes as the 36 centimeters. So this rectangle is now converted into a pipe of equivalent diameter 0.36. So Reynolds number for this is equivalent diameter into the velocity, that is already mentioned, 8 meters per second. The density of the air, that is already mentioned. The viscosity of the air, that is also mentioned. So Reynolds number, that is coming as 1,91,700. Then the Prandtl number, which is nothing but Cp mu upon K, its value coming as a 0.7. Then the heat transfer coefficient. Now the second important correlation to calculate the heat transfer coefficient is the Dietz-Boelter equation. So this is for the turbulent conditions. The Reynolds number values are very high and Prandtl number values are low. So this Dietz-Boelter equation is Nusselt's number, which is equal to 0.023 into Re raised to 0.8 into PR raised to 0.4. So Nusselt's number, that comes as the 335. From there we can calculate the heat transfer coefficient. Here we have to take into account the equivalent diameter HD upon K. Nusselt's number is nothing but the HD upon K. Now you have to remember all these numbers, because for solving the numericals you require the knowledge of the different numbers. H D E upon K, this is nothing but your Nusselt's number. So this H that is calculated as Nusselt's number into DE, Nusselt's number into the K upon the equivalent diameter. So this value of H that is coming as 24.24 watt per meter square Kelvin. Now the heat leakage per unit length per unit temperature difference. From this duct, a rectangular duct, the heat losses will be there. What will be the area through which heat transfer takes place? Is the perimeter. Now this is the Q heat leakage per unit length per unit temperature difference. Our formula, that is nothing but Q, which is equal to HA delta T, right? Q, which is equal to the HA into delta T. So this is per temperature difference. So taken on this side, delta T has taken on this side. Now area, that is per unit length, that has been mentioned. So only the surface area, that is the perimeter into the length, that will be the surface area. Perimeter into the length, that will be your surface area. So 2 times the length plus breadth into the length. This is what? The width. This is what the duct will be there. This is the duct and its length is considered as the 1 meter. Length of this rectangle is L and the breadth of this rectangle is B. And this is per unit length. Per unit running length, you can say. Don't get confused with this L and this length of the duct. This is length of a rectangle.